EMT, electrical metallic tubing, is approved as an equipment grounding conductor for buildings that are 3 stories or less in height. This approval is contingent upon the EMT being installed strictly in accordance with the requirements outlined in the National Electrical Code, commonly referred to as the NEC. The NEC provides detailed specifications for the proper use of EMT as a grounding conductor, ensuring a safe and effective electrical system. Proper installation involves several key elements. Firstly, the EMT must be securely fastened to all electrical boxes. These boxes house electrical components such as receptacles, switches, and splices, and it is crucial that they are properly grounded to prevent electrical hazards. The EMT provides the grounding path for these boxes, diverting any fault current safely back to the source. Secondly, the EMT must be securely fastened to all fittings. Fittings are used to connect sections of EMT change direction or transition to other types of raceways. Ensuring that these fittings are properly tightened and make good electrical contact is essential for maintaining a continuous grounding path. Thirdly, the EMT must be securely fastened to all other metal raceways. In some electrical installations, different types of raceways may be used in conjunction with EMT. If these raceways are also made of metal, they must be bonded together to create a common grounding system. The EMT can be used to provide this bonding connection, ensuring that all metal parts are at the same electrical potential. Fourthly, the EMT must be properly terminated at the service entrance panel board. The service entrance panel board is the main distribution point for electricity in a building. It is where the power from the utility company enters the building and is then distributed to various branch circuits. The EMT must be connected to the grounding busbar in the service entrance panel board, providing a direct connection to ground. Fifthly, the EMT must be terminated at other approved grounding points. In some cases, it may be necessary to ground the EMT at multiple points throughout the electrical system. The NEC specifies various approved grounding points, such as grounding electrodes and equipment grounding conductors. The EMT can be connected to these grounding points to provide additional grounding protection. A separate ground conductor, often referred to as a green wire or equipment grounding conductor, is generally not required to be installed inside the EMT in addition to the EMT itself when the EMT is used as the equipment grounding conductor. The EMT conduit itself serves as the primary grounding path, providing a continuous and low impedance path for fault current to flow back to the source. This is because the metallic construction of the EMT provides a highly conductive pathway for electrical current. However, there are specific circumstances where a supplemental equipment grounding conductor may be required within the EMT. These circumstances are typically outlined in the NEC and are based on factors such as the size of the overcurrent protection device, the length of the circuit, and the potential for voltage drop. It is essential to consult the NEC and a qualified electrical professional to determine if a supplemental grounding conductor is necessary for a particular installation. The NEC provides tables and calculations that can be used to determine the appropriate size of the equipment grounding conductor based on the size of the overcurrent protection device. The overcurrent protection device, such as a circuit breaker or fuse, is designed to protect the electrical circuit from overloads and short circuits. If the overcurrent protection device is rated at a high amperage, a larger equipment grounding conductor may be required to safely carry the fault current. The length of the circuit also plays a role in determining the need for a supplemental grounding conductor. Longer circuits have a higher impedance, which can impede the flow of fault current. In such cases, a supplemental grounding conductor may be necessary to reduce the impedance and ensure that the fault current can flow back to the source quickly enough to trip the overcurrent protection device. Voltage drop can also be a factor in determining the need for a supplemental grounding conductor. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment malfunction and can also increase the risk of electrical shock. A supplemental grounding conductor can help to reduce voltage drop by providing a lower impedance path for current to flow. It is important to note that even when a supplemental equipment grounding conductor is not required, it is always a good practice to install one. A supplemental grounding conductor provides an extra layer of safety and can help to ensure that the electrical system is properly grounded. In addition to following the NEC requirements, it is also important to use high-quality EMT fittings and connectors. These fittings and connectors must be properly installed and tightened to ensure a good electrical connection. It is also important to protect the EMT from corrosion. Corrosion can increase the resistance of the EMT, which can reduce its effectiveness as a grounding conductor. EMT should be installed in a dry location and should be protected from exposure to chemicals and other corrosive substances. Regularly inspect the EMT for signs of corrosion and replace any corroded sections. When installing EMT, it is important to use the correct tools and techniques. Cutting EMT can create sharp edges that can damage wires and cables. Use a pipe cutter or a hacksaw with a fine-tooth blade to cut EMT cleanly. Deburr the cut ends of the EMT to remove any sharp edges. When bending EMT, use an EMT bender to avoid kinking or damaging the conduit. Support the EMT properly using EMT straps or hangers. The NEC specifies the maximum spacing between EMT supports. Over-tightening EMT fittings can damage the conduit and reduce its effectiveness as a grounding conductor. Tighten fittings to the manufacturer's recommended torque. When pulling wires through EMT, use a wire lubricant to reduce friction. Avoid pulling too many wires through the conduit at once. The NEC specifies the maximum number of wires that can be installed in a given size of EMT. Grounding is a critical aspect of electrical safety. A properly grounded electrical system protects people from electrical shock and also helps to prevent damage to equipment. EMT can be an effective equipment grounding conductor when it is installed in accordance with the NEC requirements. It is essential to consult the NEC and a qualified electrical professional to ensure that the electrical system is properly grounded. Electrical codes are constantly being updated and revised to reflect new technologies and safety standards. It is crucial for electrical professionals to stay up to date on the latest code requirements. This can be achieved by attending training courses, reading industry publications, and participating in professional organizations. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. Electrical systems should be inspected periodically by a qualified electrical professional. Maintenance tasks such as tightening connections, replacing worn parts, and cleaning equipment should be performed on a regular basis. Remember that working with electricity can be dangerous. Always take precautions to protect yourself from electrical shock. Energize circuits before working on them whenever possible. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, hire a qualified electrical professional. Understanding the principles of electrical grounding is crucial for ensuring electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock. The NEC specifies the requirements for grounding electrical systems, including the types of grounding conductors that are permitted and the methods for installing them. The grounding electrode system is a critical component of the electrical grounding system. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provides a path for fault current to flow back to the source. The NEC specifies the types of grounding electrodes that are permitted and the methods for installing them. Bonding is another important aspect of electrical grounding. Bonding involves connecting all metal parts of the electrical system together to create a common grounding system. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. The NEC specifies the requirements for bonding electrical systems, including the types of bonding conductors that are permitted and the methods for installing them. Surge protection is also an important consideration for electrical safety. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes and other events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC specifies the requirements for installing SPD in electrical systems. Remember that electrical work should only be performed by qualified electrical professionals. Working with electricity can be dangerous, and it is important to have the knowledge and skills necessary to perform the work safely. Always follow the NEC requirements and use good electrical safety practices. By understanding the principles of electrical grounding and following the NEC requirements, it is possible to create a safe and reliable electrical system.